All right, guys. So now we'll move on to the next part of the lesson. So the next one, you are going to learn how to find the center of mass of a uniform hemispherical shell. Okay, so how do we get the center of mass of a uniform hemispherical shell? The first thing is, how do we create a hemispherical shell? So at this point, we know how to find the center of mass of a hemisphere, right? A solid hemisphere. So when the hemisphere is completely filled, we know how to find the center of mass. So that we've already done. So here you have how do you create the hemispherical shell? As you can see, what we do here is, I have here a hemisphere of radius r. Okay, and you guys can see what I'm doing here is I'm removing another hemisphere of radius x. Can you guys see? There's a hemisphere of radius r, and then what we do is we remove from this solid hemisphere. Okay, so this blue color one is a solid hemisphere. I'm removing out. Okay, I'm carving out another solid hemisphere, and that's radius is the radius of the part that I'm scooping out is x. And you can see now, in order to create a really good hemispherical shell, this x needs the radius x needs to be 1. The radius, in order to create a really good shell, the value of x, the radius x needs to be as close as possible to r. Do you agree? So if x is as close as possible to r, then you get the shell, right? Because the shell is has supposed to have I mean, the thickness needs to be really small, because if you have a higher thickness, then that's not a shell, right? So you need to have the thickness minimized as much as possible, right? This thickness, do you agree? So we need to bring our x value as close as possible to r in order to create the hemispherical shell. All right, guys. So the way we do this is actually really simple. The way we actually get the mass of the hemispherical shell. So guys, you guys can see what I've done over here. I've created this table. Can you see these the tables that we create this kind of table for object, mass, and center of mass. So this was my strategy when I was working with you guys on center of mass in M2 as well, right? So we created object, mass, center of mass, and you can see the first object that I'm taking is the large solid hemisphere. So I'm taking the large solid hemisphere, and then you can see my next object is the hemisphere with radius x. So this is the one that I'm scooping out, right? Can you guys see? And then when I take that out, I am remaining with the hemispherical shell. Can you guys see these three objects? So you have first the solid hemisphere, radius r. Then this is also a solid hemisphere, radius x, but that's the one we scoop out. And then I'm remaining with this shell. So the inside is now gone here in the third object. Can you guys see? So now we actually go to fill these other parts as well, the mass and the center of mass. So when it comes to these kinds of 3D objects, you know the mass is proportional to the volume. Okay. So the mass is the volume, and of course, yeah, the radius of this r is bigger than x, right? But it needs to be as close as possible to r. But yeah, r is the larger hemisphere. Okay. And then over here, the mass you get by using volume. So volume of a sphere is 4 over 3 pi r cube. And you can see I've used a half here. Can you guys see? The half is to make it a hemisphere. So 4 over 3 pi r cube is the volume of a sphere. Half of that means a hemisphere, and multiply by rho, because rho is the mass per mass per cubic unit. All right, guys. So mass per cubic unit is rho. So rho is what converts this to mass. All right, guys. So 2 over 3 pi r cube rho. Can you guys see? And center of mass. So now you can directly quote. All right, guys. So we have already now proved the center of mass of a solid hemisphere is at a distance 3 over 8 times its radius. So 3 over 8 times the radius of this guy is capital R. Can you guys see? So this is a similar strategy that we used in M1, M2. Okay, so we drew a table like this, right? So then the next guy also, you can see I've done the same exact story. So mass, half of the volume, right? So half of the volume and multiply by rho. So in this case, the radius is x. Can you see? So it's going to be 2 over 3 pi x cube rho. And then the mass of the resulting object, you will have to subtract, right? Because from the larger mass, you are removing this guy. So 2 over 3 pi r cube rho, you subtract 2 over 3 pi x cube rho. Right, guys? And this is the remaining mass. Do you agree? And then the center of mass of the hemisphere with radius x, that's going to be 3x over 8, right? Because you know the center of mass of a hemisphere is 3 over 8 times its radius, right? 3 over 8 times its radius. So now in this case, this solid hemisphere, this guy is a solid hemisphere, right? So in this guy has a radius of x. So 3 over 8 times the radius x. And then the final object is the hemispherical shell, and that guy, the radius is x bar. And we are trying to find x bar. All right, guys, can you see how the table was created? All right, guys. So we've drawn this table. Okay, so apologies. I think this might look smaller than this, right? So actually, this is the larger one, right? So this is the smaller one. Okay, I hope you guys can understand the logic here, right? So the mass you find it through the volume, and the center of mass is measured as 3r over 8, measured from the origin. Okay. All right. So now our task is to find the center of mass of this hemisphere, the hemispherical shell. Right. So how do we do this? So the way we do this is really similar to the technique that we work in the way we do work in our M2 class, right? So do you recall this method? So actually, we've been using this equation even in this particular in M3 as well, right? So in the previous sections when we were talking, so this was one of the main equations we used, right? So when you make a composite body, when you have a composite body, so this is the main equation we use, right, guys? Sigma mixi equal total mass into x bar. So sigma mixi means you multiply the mass of the individual object with their own center of mass. And by the way, again, for the hemispherical shell as well, you can clearly see that y bar is 0, right? We don't need to find y bar because it's symmetric around the x-axis. So this is only the you only have an x bar. You don't have a y bar, right? Y bar is directly 0 because it's on the x-axis, because there's a line of symmetry, right, guys? All right, guys. So let's now input the value. So you can see it's 2 over 3 pi r cube rho multiplied by 3r over 8. Can you guys see? So what I've done here is I have multiplied the mass with the center of mass. That's what we do, right? And then sigma means you're supposed to add. You're supposed to add the next mass with its own center of mass. However, you guys can see that I've done a subtraction. So what's the reason that I'm doing a subtraction? So in this composite body to one solid hemisphere, I'm not adding another solid hemisphere. From this given solid hemisphere, I'm removing. This solid hemisphere. So that's why, because it's a reduction, because you're removing, that's why we need to subtract. Okay, so sigma addition works if you keep on adding objects. If you keep on adding bodies, it's addition, true. But since this is you're removing the hemisphere, it must be a subtraction. That's really important. Okay, so you subtract the next mass into center of mass, 2 over 3 pi x cube rho. So multiply by the center of mass is 3x over 8. Can you guys see? So this is equal to total mass into x bar. So total mass is 2 over 3 pi rho. I hope you guys can understand how I got this right. So I just subtracted these two guys and took 2 over 3 pi and rho out. And you're remaining with r cube minus x cube. Okay, right, guys? Can you see? So, I've come to this point. Okay, and then after that point onward, it's time to simplify. So you can see I've cut off terms that are common to everyone. 2 over 3 is common for the entire term. Pi is common for all the three terms, and rho is common. So I've cut it off, and I'm remaining with over here r cube into 3r over 8. That's 3r to the power 4 over 8, right, guys? So I hope you're following me. And this one, x cube into 3x is 3x to the power 4 over 8. Can you guys see? I'm just writing the remainders. Equals, over here I'm remaining with r cube minus x cube times x bar. Right, guys? Is that clear? All right, and then let's input the, so you can see we need to simplify this as much as possible now. So I'm remaining here with, you can see I've taken 3 over 8 out, and I'm remaining here with r to the power 4 minus x to the power 4. And then you can see I've taken this r cube minus x cube to the other side as a division. That's why you get the r cube minus x cube here. Okay, this side I've taken a 3 over 8 out, and I'm remaining with r to the power 4 minus x to the power 4. And this r cube minus x cube has come down as a division. Is that clear, guys? Can you see what I've done? And then the next step of simplification is it's simply using algebra. So basically, I've done difference of two squares. So r to the power 4 minus x to the power 4, this is difference of two squares, right, guys? So this is with power 4. So when you break it up, it's going to be, you should know this stuff, right? A to the power 4 minus b to the power 4 is going to be a to the a square minus b square times a square plus b square, right, guys? You should know this stuff. So if it is a to the power 6 minus b to the power 6, it's a cube minus b cube times a cube plus b cube. So this is called difference of two squares. All right, guys? So you should be familiar with that. So r square minus x square times r square plus x square. Can you guys see? And the denominator, you have r cube minus x cube. I think you can see I've factorized this as well. And this factorization is something that you need to know. I think I have written it over here. So this might be new to some of you. So you guys might be finding the cubic expansion to be new. So then I suggest you to write this down. So this is really important. So you must definitely remember. So this is the result that you need to remember, and this is the result that you can use anywhere in your exam. So I highly suggest you to write this down, make a note of it, and definitely know about this. Okay. So a cube minus b cube, the expansion. I mean, you can factorize it in this following manner. It's a minus b times a square plus ab plus b square. So it's a little bit different than the other normal factorization. So you need to actually have this in your mind. You must know this, and this is I believe this must be a new rule for many of you, right? So this is a new rule. And if you take your time to expand the bracket, if you expand the bracket, you will get this guy perfectly. You will get a cube minus b cube perfectly. Okay, guys? So expand the bracket. Okay, and get that done. Okay, so you'll get a cube minus b cube perfectly. All right, so then I'm going to apply the r cube minus x cube equation here. So that's going to be r minus x times r square plus rx plus x square. Can you guys see? It's r square plus rx plus x square. All right, so r square minus x square is going to be r minus x times r plus x. Can you guys see? Into r square plus x square. So I've actually, again, I've used difference of two squares here. Can you guys see what I've done? I've used difference of two squares for this guy. Can you see? R square minus x square is again r minus x, r plus x. R square plus x square is remaining here. Over here, the denominator is r minus x times r square plus rx plus x square. Can you see I've written the same thing over here? The only difference is the r square minus x square. I've done difference of two squares and written it. And now you can see the r minus x is that complete factor cuts out. I'm cutting out the factor r minus x. It completely cuts out, and I'm remaining with this. Can you guys see? So this is what I'm remaining with. So this is what I get for x bar. All right, guys, are you clear until this point? All right, guys. So now to get the final answer, now you know we are supposed to give the center of mass all in terms of this, in terms of a a constant r, right? So r was the radius, capital R was the radius of our hemisphere, the hemispherical shell. So now what I need to do is I want to get this x bar, okay, in terms of r, and I told you, right, I've been telling you to create the hemispherical shell. In order to create a really thin shell, okay, you need to have what this x value needs to be as close as possible to r, right? Okay, so if x is having a big gap with r, you have a hemispherical shell with a big thickness. So if there's a big thickness, it's not a shell, right? A shell means it should have minimum thickness. Okay, so if this x value, in order to achieve that, this radius x should be as close as possible to r. Do you agree? So then all you have to do here is, guys, you can see the next step of the working. So what I've done here is as x limits or x is as x closes in on r. Okay, so because in order to make this work, our x needs to be as close as possible to r. So you limit x to r, you send x to r. Can you see? And then you replace all your x values with r. Can you see, guys? All the x values are replaced by r, and you get here r plus r. Here this is r square plus r square. Okay, so in the denominator you get r square, r into x is r into r, that's r square plus r square. So you can see you get a whole bunches of r like this, right? So r plus r on top is 2r, r square plus r square is 2r square, and in the denominator you get 3r square. Can you see, guys? and then simplify, you can see we get 2 times 2, so I have here 3 over 8 times 2 times 2, 4r cube on top and 3r square at the bottom. So simplify, cut, and you can see things cut off, the 3 cuts off, the 8 and 4 you are remaining, and there's a 2 remaining down, so we end up getting half r cube over r square is r. So basically I'm getting here the center of mass of the hemispherical shell is at a distance half r from the plane face. Can you guys see? So this is a really important result. You must be able to derive the result, and also you will be required to use the result. All right, guys. So this is how we get this particular result. So this is a really important derivation. You must be able to do this on your own as well. Okay. All right, guys. So we're done with the proof of the conical hemispherical shell, right? So this is the conclusion. The center of mass of a uniform hemispherical shell lies on the axis of symmetry and is at a distance half r from the plane surface. I think that's quite clear to everyone, right? So this distance is half r. Okay, so it's a distance half r from the plane face. All right, and then guys, the final one here. So it's a center of mass of a conical shell. So we discussed hemispherical shell, and now we are going for the conical shell. So fortunately over here, you are not required to, the proof is not given. So they have directly given you the result. So you can directly quote the result. Okay. So we'll directly go with that. The center of mass of a conical shell lies on the axis of symmetry and is at a distance 1 over 3h from the base. So you need to be able to use the result. I will be showing you how to use this result and how to work forward. But the thing is over here, so in the textbook, they've not gone for the proof. So it's quite a rigorous proof. So in that case, they've just given you the result and you are supposed to use the result directly. Okay, so you need to definitely have in memory the previous results that we've all derived. Okay, so all those should be there. So this guy, you need to remember the result. Okay, so in this guy, the conical shell, it lies on the axis of symmetry and is at a distance 1 over 3h from the base. Okay, so in textbook they have not guided you on how to get the center of the proof of this. Okay, but in the exam, in an event, if you do get something like this, they will probably give you some guidelines as to how to break the strips. So they should give you some guidelines, but right now in the textbook they have not given you anything of the sort. So we will directly go with exactly what they have given you. All right, guys. Okay,